Hello everyone, good evening. So, a quick introduction regarding the program and the professor here. So, my name is Shaman. We are from AcadFly, powered by Physics Wala. Today, we are all here gathered to take the complete course, the introductory course from Professor Deep Jariwala regarding AI, as we are all aware. So, this is the complete structure of the program will be a 2 hour program. First 1.5 hours will be taking us through the complete journey of the program, and last 30 minutes we'll leave for the Q&A, right? And post that, we'll be quickly walking you all with a particular PPT, 5 to 10 minutes for that matter, right? It will be an interactive PPT. At the end of PPT, I would request all to stay till the end, so that because at the end there will be particular reward for the we have a particular QR code which is mandatory to be filled from everyone, so that all the certificates will be distributed for you for attending this particular session from Physics Wala, right? So please make sure we all are there throughout the session till the end of the PPT, so that you need to fill that particular form in order to get your particular certificate, right? So please make sure. And coming to Professor, a quick introduction. Mr. Deep Jariwala is PhD in Material Science and Engineering from Northwestern University, and he also has BTech in Metallurgical Engineering in IIT BHU. Currently, is professor in University of Pennsylvania, and his expertise is nanoelectronics, nanophotonics, and nanomaterials, semiconductor devices, optoelectronics, condensed matter physics, materials characterization, and computing hardware, right? So, Professor Deep Jariwala, with 7 years of teaching experience across Asia and America, excels in undergraduate and graduate courses on semiconductors, nanotechnology, and device physics. With 15 years in research, his work includes notable discoveries in semiconductor physics and innovation in computing and communication hardware. So this is a quick introduction regarding Professor. So over to you, Professor.
Okay, let's get started. So I've made this presentation, which is sort of a broad overarching presentation. I was told it can be both semiconductors and AI, or semiconductors as they pertain to AI. So I tried and made this presentation. Also, the presentation is made for high school students, not necessarily for junior college students. So I've kept it at that level. Certainly, we will go into some technical details, which some of you may find slightly more advanced, but that's the whole point of the program to expose you to a little bit advanced concepts. But I've tried to keep those advanced concepts to as minimum as possible. I've also tried to minimize the equation, so to speak. Okay, so I'm hoping we'll be done in the next 90 minutes, and then I'll take some questions. I have a hard deadline to leave by 9:30 my time, since I have another appointment. Okay. So let's get started. So my name is Deep Jariwala, and thank you all for coming, and for Shamant and Acadfly and Mayank and others for giving me the opportunity. Here's my contact information. I run a large research group at University of Pennsylvania. We work in many different areas of research. These are sort of the big four areas: nanoelectronics, nanophotonics, functional imaging using both scanning probe and electron beam techniques, and then finally also synthesis of new semiconductor materials for advanced applications using, for example, metal organic chemical vapor deposition. All these are uh, uh, very standard techniques for making semiconductors. What Today's talk, of course, is more introductory general talk, so it won't be as much about my research. However, I will show you some examples of where our research is impacting these areas. So, but the focus of today's talk will be mostly in the nanoelectronics domain, because that domain is most closely related to AI and computing hardware. Okay. Okay, so without further ado, let me get started. These are basically some of the publications that we have published over the years in many journals. I'll provide another list at the end if anybody is interested in looking them up in more detail. So let me go back and address the grand challenges in modern classical computing. The challenge of classical computing is that power consumption continues to rise in classical computing. And I keep saying classical computing because there is a lot of news, lot of sort of information being thrown out in the media, on social media, everywhere about quantum computing, and a lot of people are justifiably excited about quantum computing. But I should point out to everybody very interested in quantum computing is that it is still not a reality, right? The people have been working on it for many, many years, but there is no clear product or no clear pathway to do any realistic quantum computing yet. Perhaps, maybe not in our lifetime either. That's my pessimistic sort of outlook over it. But if you look at classical computing drives modern society. Everything that is happening today, including this seminar, is possible because of classical computing. And so, what is truly happening is if you look at, there are two major challenges in classical computing, and they are sort of connected challenges. Why do I say that? Well, one is that the amount of energy required by classical computing has been rising every year. This is a graph taken from SRC. SRC stands for the Semiconductor Research Corporation. It's a consortium of all the major semiconductor companies you've ever heard about. And then the yellow line over here is the world's energy production, which suggests that the world energy production doesn't rise that fast, right? It's like even over decade, the rise in the world's energy production is like very minimal, about 5% or so per year is how the world energy production rises. Whereas the energy required for computing and communications, which is this green line, or compute energy, which is given over here, keeps rising exponentially. So this is going to become a challenge, which I will explain in more detail in the next slide. The other challenge is actually the data challenge, right? And the data challenge is pertained or is technically referred to as the von Neumann bottleneck. What it means is that as we are progressing as a society, especially as we are doing computing, AI type computing in society, our our fundamental needs of computing are changing, right? So until like about 2019 or so, or before that, our computing needs were limited by how much of computing power was available, or in other words, how many transistors were available. What has happened since then, or since the chat GPT era, I would say, is that computing has become more data centric. More data centric means you are doing less of arithmetic logic type computing. You are doing more of data interpretation like computing, which is what AI does. Pattern search, image recognition, pattern match recognition, things like that. And to do that, you basically need these models like ChatGPT that have an insane number of parameters. And these parameters are literally 1 billion, 10 billion, 100 billion, 1 trillion, 10 trillion, right? GPT-4, for example, has 4 trillion parameters, right? I hope everybody's aware GPT-4 is the latest version of ChatGPT. Whereas if you compare that to the amount of high bandwidth memory available in the AI hardware that is processing it, such as NVIDIA's H100 or H200 processor, that is available in gigabytes. Whereas what you need is truly tens of terabytes of memory to process these models. So that tells you how the hardware, which is this line, and the software, which is this line, are diverging from each other, creating the bottleneck between logic and memory. So it's very interesting how the compute era has sort of changed only in the last 3 to 5 years. So why is this important? This is important for many reasons. One is if you look at the energy forecast, this is again pertains to very similar to previous slide. The energy forecast suggests that by 2030, 21% of all electricity consumed by all of the people on the earth will be required for what is known as ICT applications, which means information and communications technology. So all of computing, basically, right? This is this is a non-trivial number, and this number was actually forecast back in 2018 before this AI boom or ChatGPT boom started, right? And once again, coming to this idea from SRC that computing and communication, the energy required from computing and communication, given in joules over here, keeps rising at at an exponential rate in comparison to, for example, the world's energy production, which just remains largely flat, right? And so this is quite important. This is something which the society needs to solve collectively, and it's not that the society has not been working on it. Okay, society has been, or people, scientists, engineers, companies have been working on these things for a while. And the way we know these things were actually progressing well is if you look at the approximate energy required per useful computation, that has been dropping also exponentially over many years, right? So all the way from 1946, when the first ENIAC, or the first digital computer, was made, to the PC, and finally today's NVIDIA's P100 GPUs or Google's TPUs, the approximate energy required per useful computation has been steadily falling. The issue, however, is the progress has been made so much in terms of optimizing optimizing the computing efficiency, that we are reaching the threshold levels. Okay, what does it really mean? It means that in the early parts of the 20th century, sorry, the late parts of 20th century, which is 1980s and 90s, most of this energy consumption reduction was driven by Dennard scaling and Moore's law, which I will also get to in a few slides. But then post 2000, post year 2000, most of the innovation has happened mostly in the architecture space, which is how did you arrange logic and memory devices on the processor, or going from the CPU like processor to GPU like processor, right? And then eventually nowadays people are calling TPU processors, which are tensor processing units. Okay. So this is where the innovation has been. But what we are reaching very soon, which is, now is here, and 2025 is not that far away, of course. So we are right around this line. We are reaching what are known as CMOS limits. CMOS stands for complementary metal oxide semiconductor. It's the technology used for modern computing. Silicon CMOS is the technology, as many of you may know, and that's sort of the physical limitation. And so, if you want to exceed this, what you want to do is actually materials and device level innovation. Unless materials and device level innovation is done, I think we are going to saturate in terms of our computing efficiency per bit or per useful computation. Okay. So the goal in life, if we are doing research in this area or trying to advance the field in this area, is to design materials, devices, and systems that maximize the number of bit operations per watt of power consumed. Okay, that's sort of the holy grail goal. Many companies are after this, or all AI companies are basically after this goal. Okay, so to understand this, we need to first understand what drives computing hardware. And so the part one basically is going to be about transistors and logic devices that actually do the computing. And then part two is going to be memory devices that store the information that allows you to do AI compute. And I'm going to be talking about some introductory work and some latest and greatest advances in both these areas. Okay. So, to get started with, instead of me talking incessantly, I have decided to pull a YouTube video. It's a short video, just 2 minutes, to inform you or to get everybody on the same page of what a microprocessor is. Because microprocessor is, or a processor is what at the heart of every AI chip, or every chip, not just AI chip. AI chips are just more bigger, more advanced versions of the same microprocessor, and what comprises of these chips. So this is, for example, a silicon microprocessor. Here is the video sort of describing with animation how it is made and what it comprises of. Okay.
Microchips combine a precise assembly of electronic components into one very small unit. They are built for an endless variety of specialized functions, and they're embedded into almost every electronic device. A microchip is protected within a case, creating connection pins going to and from the circuit board the chip is attached to. Microchips are generally used to modify analog signals or process and store digital data. Among all the microscopic wires, tiny electrical switches, called transistors, are the brain of a microchip. Transistors enable the chip to make decisions and produce useful results based on some form of input. Now let's take a look inside a microprocessor, an advanced microchip at the heart of every computer system. This type of microchip performs a logical or mathematical operation on incoming data based on instructions from software. Digital text, sound, and graphics are all represented as a highly complex collective of only two electrical states, represented as 1 or 0, called bits. These are the simplest elements of data computers work with. Incoming bits travel along a data bus, and within the processing core are operated on not by millions, but by billions of transistors. The constant switching of these transistors is interpreted into useful information. The results get passed to the integrated memory controller, which directs traffic to and from the processor. The entire cycle computes in under a billionth of a second. Now the processor is ready to work with the next set of data. Microchips form an indispensable element of our everyday lives, and each year they are being built faster, smaller, and more energy efficient. We welcome you in taking a look at the incredible world of microchips.
Okay, so I hope everybody got the point over here. The important point to get over here was that there are billions of transistors switching at speeds of gigahertz, which means every nanosecond they are switching. And this allows you to do all these computations or run the logic gates that actually processes your computing instructions and put it out back to the software. Uh, okay. And so the question really is, after looking at the video, what really are transistors, right? And what do transistors do? And I'm going to take you over a little bit of the history of transistors, about the operation of transistors. Where are transistors today? Where are they going to go next, right? In terms of new materials, new types of structures, new types of operation, introduce a little bit of my research, and then we'll move on to memory devices. Okay, so in very simply speaking, transistors are electronic switches that do the computing, logical ones and zeros, as well as amplification. In some cases, this was highlighted in the video as well. There are two primary types of transistors. The very first transistors that were actually invented was the bipolar junction transistor. It was invented in 1947 at the Bell Labs, which is about 1.5 hour drive from my home. The second type of transistor is called the metal oxide semiconductor field effect transistor, MOSFET. This was conceptualized much earlier, I think in 1925, even before the bipolar junction transistor, by Julius Edgar Lilienfeld. But it was actually demonstrated much after the bipolar junction transistor, almost 10 years after the bipolar junction transistor. And this is the dominant technology today. In fact, all of your computers contains billions, multi-billions of these transistors in extremely small forms as small as about 10 nanometer in dimensions, as I will show you in the coming slides. So this is how transistors look like. We will be mostly focusing on the MOSFET because the BJT is a slightly old technology now. It's not quite used in most applications. Okay. And so, even before transistors were made, computing was happening. In fact, in my own department, the ENIAC was made. ENIAC, as some of you may know, was the world's first digital computer. ENIAC stands for Electron Numerical Integrator and Computer. It was the world's first computer made in my department. At that time, there was no semiconductors. Okay, so without semiconductors, how would you make computers? Well, back then, people figured out how to do computing using electronic switches known as the vacuum tubes or vacuum triodes. Okay, each of the vacuum triodes looks something like this. So, if, for example, each vacuum triode is as big as the palm of your hand, imagine wiring up hundreds and hundreds of vacuum triodes to make a computer. It would be not only huge; it would occupy the entire basement of the building on in which my office is currently. But it would whenever you turn it on or power it on, it would consume so much power that the entire electricity of the neighboring areas had to be cut off just to power that computer. This was back in the 90s, so before 1947. In fact, this was the situation. Okay. And now, post 1947, since the point contact transistor or the solid state transistor was invented by the Bell Labs, things changed quite a bit. It was a very momentous discovery because for the first time, we figured out how to control electrical switching in in a solid state semiconductor material instead of a vacuum, right? Switching in vacuum usually requires much higher energy, much higher voltages. To do it in a semiconductor is very transformational because now you can do it on a piece of silicon wafer or a piece of germanium wafer and do billions of them together and connect billions of them together. So that was sort of the big jump or leap forward, right? And so this was, of course, invented by these three great people, three inventors of the transistor, William Shockley, who was the leader of the team, and then John Bardeen and Walter Brattain, right? They all won the Nobel Prize in Physics in 1956 for it. After inventing the transistor, Shockley actually moved to California to start Shockley Semiconductor, and Shockley Semiconductor was the precursor company to Intel, AMD, and all of these other big semiconductor companies. And this was basically the birth of Silicon Valley, right? The Silicon Valley was started by starting Shockley Semiconductor. The Shockley is in many ways the grandfather of Silicon Valley, but the root invention, which is the transistor, happened on the East Coast, at East Coast of USA, which is at Bell Labs. Okay. Right, so let's talk about bipolar junction transistor. This was the bipolar junction transistor was the one that was invented by these three gentlemen at the Bell Labs. And then and then what we can do is we can walk over how the operation of bipolar junction transistor, and then move on to field effect transistor. So I'm not sure, but I hope that many of you are introduced to the concept of p-n junctions or semiconducting p-n junctions in your schools. Basically, semiconductors can have two types of polarities: p polarity and n polarity. This is dictated by the doping type, and they can have this polarity similar to magnet polarity, such as magnets have north pole and south pole. Semiconductors can have p type, positive type, and negative type in their doping. And so when you bring p-type and n-type materials together, you form a p-n junction. P-n junction is the basis of a diode. Diode, as we know, is ubiquitous in modern technology. For example, the LED is a diode, the photovoltaic cell is a diode, the photodetector is a diode, the camera is basically all p-n diodes, right? But when you take two diodes, right, and like sandwich them together to make an NPN and PR or PNP structure, you form an electronic structure that looks like this. Okay, so in other words, you have an n-type semiconductor on one side, n-type semiconductor on the other side, and in between you have sandwiched a p-type semiconductor. What it means is that if you look at the Fermi level for electrons in the semiconductor, again, this is getting a little bit technical, but I hope some of you have a basic understanding of this. If you look at the Fermi level, then electrons are in high concentration on both of these sides and are low concentration in between, which means electrons cannot flow from this side to this side unless this barrier, this gate, so to speak, can be lowered. Okay, and so this is basically the function of a transistor, that the transistor is a barrier control device. It prohibits the flow of charge or electrons from one side to the other, or allows it depending on what is the height of the gate or the barrier. And so the contacts made to the transistor are the following. This is again very well known. If you have taken a little bit of basic electronics, there is an emitter contact, there's a base contact, there's the collector contact. Okay, that is made on the transistor. And then when you apply voltage in the following way, basically the first p-n junction, this one, is a forward bias p-n junction, and the second p-n junction, which is this one, are called the base collector junction, is a reverse bias p-n junction. Okay, so the one is forward bias, other is reverse bias, and this leads to large flow of current. Okay, depending on the voltage you apply over here, the current over here can be severely amplified or cut down. And this is how, for example, you would control current flow through a transistor or switching through a transistor, right? So this is how the bipolar junction transistor works. Of course, bipolar junction transistor is not widely used today. That's because it is inherently a slow device, right? And for high speed switching in modern computing, it gave way, or it's made way to, for example, the field effect transistor. Okay. Okay. Okay, this is not okay. Sorry, I was checking the messages. It seemed like there was a message, but no. The next type of transistor we're going to discuss is the metal oxide semiconductor field effect transistor. This is the dominant technology today, called MOSFET, right? And MOSFET again comprises of similar types of junctions, which is a NPN or a PNP junction. So technically, it's not that different from, for example, a bipolar junction transistor, except now in the P-type region, which is here, the channel region as we call, there is actually an insulator. Okay, and this insulator region allows you to dope to dope the semiconductor based on the voltage applied. And so if you now wire up the MOSFET, what ends up happening is that you have your three electrodes, which are called differently. Earlier they were called emitter base collector. Now they are called source gate drain, right? And so the gate electrode in conjunction with the semiconductor is basically like a capacitor, right? So what you're doing is you're charging and discharging a capacitor, and as a function of charging and discharging a capacitor, you are allowing the amount of charge to flow through from source to drain, and this encodes your information basically. So as we were saying earlier, all of the computations happen on information which is zeros and ones. So what is a zero signal? What is a one signal? Well, where the capacitor is discharged and no current is flowing, that's a zero signal. When the capacitor is charged and the current is flowing, that's sort of a one signal. And this happens extremely fast in the time scale of nanoseconds to even picoseconds. And therefore, the computing happens at a very rapid rate. Okay. So for example, here is what I'm showing you, that when a MOSFET is off, certainly there is zero voltage applied. So voltage applied at the gate is equal to zero. Therefore, the barrier stays. There is no current flowing. But when you start applying voltage, the barrier starts reducing. And as the barrier starts reducing, current starts flowing. And when you have applied a voltage, a much higher voltage than zero, the barrier is completely gone. The current can flow in predate. So MOSFET is basically on. So you can turn these MOSFET between off and on states like this, right? By changing through different voltages on the gate. And as you change through the voltages on the gate, you can turn it off, on, off, on, off, on, and so on. And that's how computing digital zeros happens. So what I just did on the slides, off, on, imagine this is happening 1 billion times a second, right? So yeah, that's the rate at which computing happens. Okay. So then the big question is, how many transistors are there on modern chips, right? So we talked about transistors, we looked at the video of microprocessors. The important question to ask is, how many transistors are there on modern chips? And this is governed by what is known as Moore's law, right? Moore's law was postulated by the famous Gordon Moore. Gordon Moore sadly passed away last year, right? But Moore's law, he was the co-founder of Intel, but he postulated in Moore's law that the number of transistors on a microprocessor is going to double every 18 months. And this law has largely held true back when it was postulated in the 1970s to today, which is, well, 2020 is not today, that's close to today. You can see that the number of transistors on chip have steadily increased. The latest microprocessors from NVIDIA, for example, on NVIDIA's AI chips have about 80 billion transistors. Okay, 1 billion is about 100 crores. For those of you who keep a track of our track of it in Indian counting units, like crore is an important metric in Indian units. So 1 billion is 100 crores. So for example, 100 billion, which is what is there on modern NVIDIA's AI processors, we are talking about 10,000 crores. So 10,000 crore transistors are there on modern AI chips, which is an enormous amount. That tells you how small each transistor is, right? So that's where we stand in terms of number of transistors. If you look at the modern transistors today, they actually are approaching the dimensions of just a few atoms. So for example, this is a cross section of a modern transistors, right? A cross section of a modern silicon transistor where this is taken using an electron beam micrograph. What you can see as you zoom into this, the very end of the transistor is you can start seeing individual atoms, right? And the width of this transistor, this is also still old from several years ago. I think this is 2018 or 2017 transistor. Right, we are talking about widths of about 4 to 5 nanometer. Each of these bright dot over here is an individual atom, for example. So you can see it's a dozen atom across, right? And it is several dozen atoms tall. And that's sort of the dimensions of modern transistor. That tells you how small they have made it. Okay. And again, all this is an ingenuity of the modern semiconductor technology. I offer a separate course, a separate lecture on how to make the semiconductor chips by micro and nano fabrication. That won't be covered in this particular course. But this is more about giving an introductory flavor. So based on this, how transistor scaling is involved, it's worth investigating how has the microprocessor architecture evolved over time. And even there, you can see a paradigm shift happening somewhere around 2005. Okay, so around 2005, something very interesting happened. The Moore's law, in principle, continued, and it still continues to date. Okay, if you stick to the standard definition or the very colloquial definition of Moore's law, the number of transistors should basically increase, right? It does not follow the strict definition of Moore's law that Gordon Moore himself had postulated, but that's a separate argument, a discussion for another day. But if you look at around what happened around mid 2005 is that the speed of the microprocessor saturated. Okay, it's saturated at a few gigahertz, for example. Okay, this is a scale in exponential scale, frequencies in megahertz. So this is saturated a few gigahertz. Okay, because this is about 1,000, so this is a few thousands, a few gigahertz. Okay. Then what happened is, in order to improve computing power, we started going from a single core to multiple core processors. So that was happened around 2005, and about we gave way to dual core, quad core, and now there are hundreds of cores in a microprocessor. So we went from a single core to a multi-core era, and you can see there is a very natural transition of that right around 2005. Okay. And so this is where we stand today as a community. We have made microprocessors very big, very complex, billions of transistors. And we have reached a point where improving energy efficiency has become more and more difficult. And so the latest developments that companies want to make in this regard is actually to introduce new materials, take it beyond silicon, okay? Take it beyond silicon so that the new properties of new materials can enhance the microprocessor. So this idea of using low dimensional or nanoscale semiconductors for computing and microprocessors has been around for a long time, because even before 2005, in the 90s itself, Intel and several other semiconductor companies sort of understood that we will reach a limitation of silicon at some point. So the question is, what do you replace silicon with? Are there competitive enough, okay, are there competitive enough semiconductors out there that you can replace silicon with and that could actually perform better than silicon? And so this has been an investigation going on for many years. The entire research community, or the materials science or electronic materials research community, has been focused on it for more than 30 years. Various type of semiconductors have been investigated. The most popular ones are 3-5 semiconductors, such as quantum wells of 3-5 semiconductors. Again, I'm not going into the details of all of this. I offer a much longer course, about 5 to 10 hours course, where I walk over semiconductor physics first, or the basics of semiconductor physics, how to identify, how to make semiconductors, and then talk about devices. This is more of an overview program or an overview lecture, right? So I can't get into details of all of this. There's not enough time. But the 3-5 semiconductors are examples are gallium arsenide, indium arsenide, indium antimonide, and so on. They operate or they move electrons at much faster speeds as compared to silicon. So maybe they are an option. There are plastic or organic molecules and polymers, they were investigated at some point because they are so small, you could make transistors even smaller. But it was found that they don't conduct electrons as quickly as silicon, so they have been ruled out for now. There were hybrid materials also looked at some point, but they have also been ruled out because electrons don't move any fast. Colloidal nanocrystals or quantum dots from colloidal nanocrystals were also looked at, but even they cannot be scaled to large areas, so they have a problem. The two most um, important semiconductors in this regard that are currently being investigated by the industry, which could be potential replacements for silicon, are 2D semiconductors such as transition metal dichalcogenides and then carbon nanotubes. Carbon nanotubes, many of you may have heard about, they have been around for a long time. They were actually discovered in 1991, so long back. They are tiny ropes or tiny tubes of graphitic carbon. Essentially, you can think about them as tunnels or highways for electrons. Electrons can zip into these tunnels at extremely fast speeds. The whole name of the game in microprocessing or semiconductor computing is how fast you can move electrons and control them to do the computing, right? And so these two are sort of the leading candidates, okay? So I'm going to focus on 2D materials because that's what most of our research is around. Of course, we also work on carbon nanotubes, but I'm going to tell a little bit about 2D materials first. So what are 2D materials? Why do we care about them here? 2D materials are a broad class of materials. There are now thousands of materials identified that can be called as 2D materials. 2D, as the name suggests, is two-dimensional. Okay, D stands for dimensional. Why do we call them two-dimensional? Well, because they are extremely thin. How thin? Just 1 to few atoms in thickness. The most popular or well-known 2D material is graphene. Graphene is a single layer of graphite. Graphite is your pencil lead. If you're using still traditional pencils, the pencil lead is graphite. Each atomic layer of graphite is called graphene. Graphene is semi-metallic in nature. It's not really a semiconductor. Hexagonal boron nitride, which is basically white graphite, is insulator or a wide bandgap semiconductor. But then there are some materials called metal chalcogenides. They are compounds of metals and chalcogens. Chalcogens are basically sulfur, selenium, tellurium. And they can also occur in this two-dimensional form. They are about 3 atoms in thickness. And then they are also semiconducting in nature. So these are the ones that are potentially touted to replace silicon in maybe the coming decade, maybe more, maybe never. Depends on how the technology evolves. Technology is moving so fast and there are so many factors under consideration. It's hard to pinpoint what will exactly happen. So why are they important in modern microelectronics? I will give the more technical reasons in the next slide. But the qualitative reasons are the following. They are extremely thin materials with van der Waals bonding across interfaces. So they don't have very strong bonding across top and bottom interfaces. So you can think about them as stickers. You can peel a sticker from one side and put it on the other side. So you can keep putting stickers on various surfaces. This unfortunately is not easy to do in the materials world, but with these kind of materials, it is easy to do. They are like cut and paste stickers, right? This allows you to build electronics in a much more compact way. Without worrying about interface issues, okay? They can exist as very high quality materials at very small thicknesses with very high chemical stability. And this perhaps is the most important point, is silicon you cannot thin down to these small thicknesses. If you start thinning down silicon to these thicknesses, it will just disintegrate, fragment. So silicon cannot exist as these small thicknesses. It won't even stay chemically stable. Okay, so therefore you want materials that will remain chemically stable at these small thicknesses, because as you are shrinking transistors, you are also making the silicon's thickness smaller, which is a potential issue, right? And so therefore these come to be of more value than silicon at extremely small dimensions. And finally, they can support very large electron densities, and electrons can potentially move faster in them as well. And these are the reasons why 2D materials are important as next generation materials for microprocessors. Okay, so what is the clear advantage of using 2D semiconductors? Again, I'm going to go a little bit technical for the next few slides. I hope it is not a deal breaker for most of you, but a metric on which you want to measure how fast, how electrons, or how good a semiconductor is for microprocessor, you want to look at the mobility of the electrons in that material. Mobility means it's a technical metric for the speed at which electrons propagate or electrons move inside semiconductors. You can see something very interesting over here, that as you reduce the thickness, silicon actually becomes worse. The more thickness you reduce, silicon becomes worse. In other words, the speed of electrons in silicon reduce as you reduce the thickness of silicon. Whereas if you look at 2D semiconductors like MOS2 and WS2, these are the popular 2D semiconductors, WSE2 is another one, the speed of electrons actually increases as you reduce the thickness. Okay, so when you go to thicknesses of about 1 nanometer or so, these 2D semiconductors are actually more superior to silicon. Okay, the same is true for mean free path, which is the longest path they can propagate before they can before they get scattered, is also larger for 2D semiconductors compared to silicon at these very small thicknesses of 1 nanometer or so. So based on this, several people have done various calculations and estimations of how computers or basic computing logic gates will made out of 2D semiconductors will operate, and how will they compare to silicon. So here is a graph. Okay, here's a graph with two axes. The first axis is power consumption. It's called as a power delay product. Okay, again, those of you who have taken circuits a little bit, you may understand this. It's called a power delay product. It basically tells of how much power is consumed per cycle of computation, right? And in this, these yellow or orange points over here, these are all silicon's projections. Again, this is a slightly old graph, but these are silicon's projections that keep going down like this. Okay. And then these projections, the red ones and the green ones, are from 2D semiconductors. Okay. The x-axis is the time of switching. And time, as you know, to what is in PS. PS means picoseconds. Okay. Pico is 10 to the power minus negative 12 seconds. Okay. 1 picosecond is 10 to the power negative 12 seconds, right? So this is 1 picosecond right here. So the prediction is that if you were to make microprocessors or logic gates out of 2D semiconductors, they could be less energy consuming and faster compared to silicon microprocessors, at least for some of these designs. And therefore, especially in terms of power consumption, they are much more beneficial. And so this is something that has been very exciting for the community to use 2D semiconductors in microprocessors. And so this is not some kind of fiction that I'm talking about or things that is only based in the lab. If you look at the latest generation of transistors that Intel is showcasing at research conferences, so as part of my work, I also have to travel to various research conferences where companies present, other researchers present, and so on. So we get to see what is the latest and greatest developments that are happening, right, in all of these places. And so one of the things that we see is that Intel recently announced that they are making what are known as silicon nanosheet transistors. In these nanosheet transistors, the width or thickness of silicon is barely 4 to 5 nanometers. So we are approaching this limit where the silicon thickness in the transistor is reducing to a very, very small dimension. And so it is not inconceivable that in future you can actually replace silicon with these sheets that are just 3 atoms in thickness. So for example, TSMC, which is Taiwan Semiconductor Manufacturing Corporation, has been talking about using 2D semiconductors in microprocessors, and they have also started developing a process that shows how to integrate MOS2 and WS2 type 2D semiconductors in the latest and greatest extremely small dimension transistors. Okay. There is another approach to reducing energy consumption by the transistor or energy efficiency of the transistor, which is the approach my research lab is taking, and we have made some breakthroughs in this regard. Again, this will get slightly technical, so please bear with me as I walk through this. I'm happy to take any questions on this later on. But this approach is known as tunneling field effect transistors. Okay. Tunneling field effect transistors involve the use of quantum mechanical tunneling as a mechanism to conduct electrons. Earlier, we looked at barrier lowering and raising. This was controlling the flow of electrons. In tunneling, you are reducing the width of the barrier. Okay, if you're reducing the width of the barrier, something called as quantum mechanical tunneling happens through the barrier, and this actually controls the flow of electrons. So you're not going over the barrier, you are going through the barrier. And this is very interesting concept because it lies deep inside quantum mechanics. But we are not going to go into that detail. But that concept leads to some very interesting properties in the device performance. So, for example, if you look at the standard transistor, which is MOSFET, this is the blue curve. The standard transistor has some slope of change in current versus voltage. The slope of change in current versus voltage is known as the sub-threshold swing, or SS. Okay, the sub-threshold swing is a metric that tells you how much energy or how much power is consumed per cycle of computing, or per cycle of switching the transistor from on state to the off state, or off state to the on state. Okay, now, if you consider the red curve, which is the tunneling field effect transistor, this slope can be arbitrarily small. In standard MOSFET, this slope is limited by thermodynamics. And at room temperature, thermodynamics limits this slope to about 60 millivolt per decade. This is the best you can do. Intel's best transistors are operating today as 65 millivolts per decade, which is extremely close to the thermodynamic limit. Okay, and so if you look at tunneling field effect transistors, they can go arbitrarily small, arbitrarily lower, right, than the 60 millivolt per decade thermodynamic limit. And therefore, in principle, tunneling field effect transistors can be way more energy efficient than the MOSFET. Okay, the issue, however, with tunneling field effect transistors is that whenever people have tried to make them, the on current density, the current density in the on state, which is here, of tunneling field effect transistors, has been lower than the MOSFET. Okay, and so this means that they add to more resistive the line in the circuit, and this leads to overall speed of the microprocessor to also reduce. So the goal is, how do you take the red curve and take it above the blue curve on both across the board of gate voltage? Okay, so you not only want it to be steeper than the blue curve, but you also want it to be higher than the blue curve. And so to do that, if you look at the structure of the tunneling field effect transistor, what people have long postulated is, what if this intrinsic region, this region that we are actually gating and reducing the tunnel barrier, can be made out of a 2D semiconductor? Because if you can make it out of the 2D semiconductor, you can have much larger electrostatic control over it, and you can control the barrier width much more effectively, therefore raising the red curve above the blue curve, achieving this goal. This has been a goal for more than 20 years. Most people have not been able to do it successfully. Our group has tried and succeeded to some extent. We have tried doing this using what is known as indium selenide. This is another type of 2D semiconductor. It is just 4 atoms in thickness. You take tiny crystals of this material, pair them with silicon. Here is an electron micrograph showing you atomic scale, like each of these bright dots are indium atoms, and the less bright dots are selenium atoms. So you can actually visualize this inside an electron microscope all up to the atomic scale. You can also visualize silicon, and each of the atoms of silicon, all these bright dots that you see, it's a checkered pattern you can see, but every bright dot is a silicon atom, right? You can visualize this pretty well. If you look at the transistor characteristics, it has slope which is almost straight line, almost vertical straight line. So it's extremely small slope of switching, making it very, very efficient as a transistor. Again, I don't want to go into too much details of this. I just want to make the comparison that if you compare this tunneling transistors compared to the standard transistor, you can live below the 60 millivolt per decade for several decades in current, potentially making it a ultra fast, ultra low energy switch, which is what we demonstrated a few years ago now, which was published in Nature Electronics. So that brings an end to the part one of the talk, which is mostly related to logic devices. Again, remember, logic devices are these transistors that process your ones and zeros. They are the heart of your microprocessor, processing ones and zeros. But as you process ones and zeros, the computation is very long in most cases. You have to store the ones and zeros derived in the middle of a computation somewhere, and then the next part of the computation has to access those one and zeros and then proceed the computation further. So to store those ones and zeros somewhere, and ultimately to store your data or data files somewhere, you need memory devices. And so memory devices are the second part of computing, which are equally important. And for AI computing, you will notice that memory devices are one of the most important things, which is where most of the innovation is happening. Actually, there is less innovation happening in AI hardware in terms of the processor. More innovation is happening in terms of the memory devices themselves, okay? And architecting memory devices together with the processor. So we're going to talk and listen to a little bit about it. Towards the end of this, I will also tell you about some of the memory device research that we are doing in my lab, right? And then I will end the program with a couple of interesting videos on where AI hardware is today and what people are looking at in big companies like Amazon and Nvidia. Okay, so if you look at the current structure of microprocessors, current structure of microprocessors is actually lateral. Okay, everything is situated laterally on a package substrate, and then you have a processor, you have SRAM memory, DRAM memory, and non-volatile memory. This is the storage class memory. This is your hard drive, for example. This is your RAM of your computer. You may all be familiar if you've opened up a computer. SRAM you will never touch, because SRAM is typically packaged together with the processor. DRAM are the RAM sticks that you're pulling in and out of your computer typically, right? And then this is the storage class memory. This is your hard drive. This is your processor core. If you look at the distances traveled of the data between them, between SRAM and the processor 2, you're traveling millimeters to centimeter scale distances. Between processor core and DRAM, you are also traveling long distances of the order of centimeters, right? So you are shuffling information over very long distances. This is potentially not great, right, in terms of doing AI compute, okay? Um, and then of course you're not using storage class memory for any computing applications, but you are storing the data over there. Now what ends up happening is that, as we have seen, the energy efficiency of computation has been limited by the architecture. This architecture has been very limiting, and we have already reached the extreme limits of how far you can go with this kind of a lateral architecture. What is truly desired in the future, this is the future architecture that I am showing over here, um, you will have a vertical microprocessor. So the vertical microprocessor would be such that the bottommost layer are just silicon CMOS, and the subsequent layers going one on top of each other. These will all be memory devices, various classes of memory devices. Imagine a tall skyscraper building with the bottom floor as silicon microprocessor, and all the above floors, starting from first floor to the nth floor, are all memory units. And there are not one elevator, two elevators, but there are hundreds of elevators moving residents from the top floors to the bottom floors at very fast speeds. That is how you would envision a a microprocessor of the future. You are building it vertically with the bottommost layer of silicon microprocessor or the silicon logic gates, and the above layers to be memory units where you are storing all this information. Okay, so this is what we want to get to. To get to this, what you need to do is you need a special type of memory. This special type of memory is called back end of line memory. Now, what does back end of line mean? Well, microprocessor structure is divided into front end and back end of line, right? And in the front end of line, you have silicon CMOS, okay, the silicon transistors, and back end of line you typically have interconnects or wires connecting various parts of the processor. And so in back end of line, there are limitations on thermal budget and chemical budget of what you can do, such that the front end does not get disrupted. And so if you want to install memory in the back end of line, you have to do it at temperatures of 400 degrees Celsius and below. And this has typically been extremely hard to achieve, and therefore this kind of microprocessor has been difficult to build, though a lot of research is going on in that regard. So let's try and understand why this memory bottleneck is so hard, or such a critical thing to solve. If you look at the processor performance over the last several decades, this is again an old chart, but it gives you the point. Over the last several decades, excuse me, you do see that processor performance has gone up by orders of magnitude, right? By orders of magnitude, processor performance has gone up. This is largely thanks to Moore's law. But if you look at memory performance has is not scaled in the same way, and there is actually a large gap between the processor performance and the memory performance over the last many years, right? Led to is that um, what this has led to is that the gap in processor and memory performance means the CPU or even the GPUs are sitting idle most of the time. Okay, they are sitting idle, they are not processing information, and most of the time is being spent reading the information from the memory and writing the information back to the memory. This means they are consuming a lot of power, and they're also being slow. And so, especially for data heavy applications like machine learning and AI, the processor is sitting idle most than 90% of the time. So, what you truly need is a dense, tightly integrated, low power, and fast memory technology. Getting all these together in one memory technology is extremely hard. It's been a challenging problem for many years now. Okay. So again, I wanted to show a standard motherboard. Here is the processor. Here are the RAM memory. As you can see, there is a long distance between the processor and the RAM memory. So shuttling billions of bytes of data between these two becomes the bottleneck in computing. So now there are various types of memory devices. As I was alluding to you earlier, there are the memory devices that you use for computing, and there are memory devices that you use for storage. The memory devices that you use for computing, they are typically less dense, but they are very fast. Okay, and they are volatile in nature, which means they actively consume power. The device that you use for storage is flash, which is your hard drive and your flash drive, right, or your USB key drive. These are typically much slower. Okay, they operate in the millisecond time range, but they are much more dense, which means a lot more data can be packed into them. As you can see, you cannot have the best of both worlds together. So if you want the best of both worlds together, then you have to invent a new type of memory that can be both fast and can store data at very high densities. This has been hard to do. A lot of people are doing research on this. So these gaps are what people doing research are trying to fill in when people are researching memory devices. For example, my group works on FEFET, FERAM technologies and FTJ technologies in all of these areas. Okay. Okay, so these are some examples of non-volatile memories. I'm sure many of you have seen all this. Um, there are major differences between a non-volatile versus volatile memory. Volatile memory, of course, when power is turned off, the data goes away. This is typically SRAM and DRAM memory. In non-volatile memory, the data retains over there. They are slower than volatile memory. These are, of course, faster. The volatile is much faster. Non-volatile is much slower. Volatile has less storage capacity. Non-volatile has much larger storage capacity. The CPU does not have direct access to non-volatile memory. CPU has direct access to non-volatile memory. Therefore, it is the primary compute memory, right? There can be both read and write. Most non-volatile memory can be only read, but nowadays you do have both read and write memory. This has a high impact on systems performance. This has a high impact on system storage, and so on. So the data in the programs that you are processing, right? Uh, 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 that you're processing and can be fetched by CPU are stored in volatile memory, and the data that you want to store permanently, they are available in non-volatile memory. Okay. So there are many emerging memory technologies out there that people are trying to put in to microprocessors. These are all back-end of line compatible memory technologies, for instance, right? And there are a few of them that I will describe over here, and then I will focus more onto the memory technologies later, which we are researching us, which are known as the ferroelectric memory technology, right? So of the four technologies listed over here, this is called as the RRAM technology or resistive RAM technology. Resistive RAM is where a filament forms as you apply voltage between two pieces of metal and a semiconductor is sandwiched in between. This filament formation changes the semiconductor from a high resistance state to a low resistance state, and breaking the filament takes it back to a high resistance state, so you can switch between these states. Similarly, you can do something with a phase change material and make a phase change memory device where as you apply current through the material, the phase of the material gets transformed by resistive heating from a high resistance state to a low resistance state, and that's how you can also get memory function over here. The last two type of devices over here are basically magnetic tunnel junctions and ferroelectric memory devices. In magnetic tunnel junction devices, depending on the resistance, the polarization state of the magnet, whether it's north-south or south-north, the resistance between the metal electrode changes, and this leads to memory storage. Similarly, in the ferroelectric case, ferroelectrics are basically electrical equivalents of magnets where polarization of the crystal can be upstate or downstate, and depending on the polarization of the crystal of the semiconductor, you can have a high resistance or low resistance flowing through, or high current and low current going through, and therefore you can store memory or information that way. Okay, so all of these devices are technically called memristors. Okay, memristors are a fundamental electrical component that you may or may not have heard of. You may have heard of the resistor, the capacitor, the inductor, but there is one thing that has been missing for a long time, and that is the memristor. That has now been discovered, or it was discovered back in 2009. It is comprised of a semiconductor which is partially doped and partially undoped. And as you cycle current through it, the resistance of the device changes. Okay, it's a nonlinear resistance. Its resistance changes with the amount of current pass, and it is achievable through a variety of physical mechanisms, which are explained in the previous slide. But memristor, as the name itself suggests, it contains the memory of the resistor. Therefore, it's called memristor, and it has the ability to store the memory of the resistance. It was first theorized in 1970s by Leon Chua. Leon Chua is a famous professor at UC Berkeley. As you know, from the fundamental units of electricity, which is voltage, charge, current, and flux, we have the resistor that relates voltage and current. We have capacitor that relates voltage and charge, and we have inductor that relates current and flux and charge are connected by the memristor, right? So this was the missing element that was postulated by Leon Chua back in 71. Of course, it was only discovered in 2008, and this was done at HP Labs by Stanley Williams. This was done using a doped and undoped titanium oxide, or a combination of doped and undoped titanium oxide. Titanium oxide, of course, is a semiconductor, and as you apply increasing amounts of voltage to it, you can actually move the ions inside titanium oxide from one side to the other, forming a high resistance state. And if you apply the opposite bias, you can again just redistribute the ions, going back to a low resistance state. And so if you apply smaller amounts of voltages or current, you will read only the doped or the undoped state, or the high or the low resistance state. But if you apply large amounts of voltage or current, you can actually flip the state and reprogram the information inside the memristor. Okay, so there are several advantages of the memristor, right? As I said before, memristor is a non-volatile memory device. It's not a volatile device, right? It can be scaled down to atomic level, so it can be made to very, very high density of memory, which is very good. Using carbon nanotubes or 2D materials, you can really slow down, or not shrink down its dimensions. It can potentially also offer very low cost integration with the microprocessor, and therefore it will potentially help overcoming the von Neumann bottleneck, which is the logic and memory bottleneck that we talked about. However, this technology is not perfect. It is still being researched. Some microprocessors are available and for limited applications that have embedded memristors in them. But there is still many problems with the memristors, such as device variability is still large. That's because the switching is largely a stochastic process, right? And then it also requires scaled up architectures and CMOS integration, which has not been fully worked out. Okay. So in this concept, in this context, my research group has been working on ferroelectric diode memristors. These are new types of memristors that we have been working on. They not only have the memristor property, but they also have the inbuilt diode-like property. They have very high performance as a result, and they are made out of this novel ferroelectric semiconductor that we are working on, known as aluminum scandium nitride. Okay. So what is the advantage of a diode-like memristor as opposed to a standard memristor? I mean, diode-like memristors have these nonlinear diode-like properties, whereas standard memristor has symmetric hysteretic properties. So a standard memristor has to be paired together with a transistor in a microprocessor, whereas the diode-like memristors can stand by itself. So there is no need of a selector transistor as a result, and therefore it eliminates fabrication complexity through 3D vias in stacked back-end of line memory array. As you saw in the microprocessor video earlier, there is a forest of wires that goes on top of the microprocessor. If you have to reduce the density of wires over here, it only helps in the reducing the fabrication complexity, for example. So if you have these kind of memristors, you can also do computing within the memristor itself. This is a very emerging area of computing hardware known as compute in memory. Normally, computing is only done in the processor, but nowadays people have figured out how to do some kind of computing, not general purpose computing, but some kind of computing within the memory itself. And so this kind of computing you can think about as searching, sorting, pattern matching, right? So not multiplication of matrices, but searching is certainly that can be done. Searching is a very important application in modern computing, especially in AI, right? And so this architecture that you can make out of memory is known as TCAM, or ternary content addressable memory. If you were to draw the circuit diagram of something like this using silicon transistors, it will require 16 silicon transistors. Okay, so 16T CMOS architecture. If you were to do it with standard memristors, you would still require two transistors and two memristors. But if you were to do it with ferroelectric diode memristors, you will only require the 2R or two ferroelectric diodes over here. So this becomes a very powerful architecture because you got rid of the transistors, so it becomes extremely fast, extremely efficient. We have already demonstrated that the search delay you can have using this kind of architecture can be as low as just hundreds of picoseconds, and the cell area can be extremely small as well. This helps reduce the energy consumption, and as both in searching as well as writing, right? So this is actually a huge progress forward. Certainly the speed is much high because the search delay is much low. So this concept that we invented and presented at the Bell Labs, we actually won the Bell Labs prize for it a couple of years ago in 2022. Now turns out the memristors, or most memristors, can also act and in an analog way. What I mean by that is you can pulse program them to gradually change their resistances. So as you apply pulses, you can gradually change their resistances and then flip them back to the original state, or you can gradually program and deprogram these memristors. This kind of gradual programming and deprogramming of the conductance, this type of analog programming and deprogramming, is actually very powerful um, uh, because a lot of biological systems, namely neurons in the human brain, function this way. And this is why they are called artificial neurons or artificial synapses. A lot of memristors are called artificial neurons, artificial synapses, because they open the door to an even more exotic style of computing, very important for AI, known as neuromorphic computing. So let's take a deep dive, or if not deep dive, at least a shallow dive, because we don't have too much time remaining, to understand how is the computer, the modern computer, different from the human brain. So I think it's worth understanding over here. And when we are getting to very advanced AI as a society, so it's worth understanding at a fundamental level how is the human brain very different from artificial brains or silicon brains that we are making. And note that every system today that operating in the world, every AI system still uses fully digital signals. Okay, whereas the human brain uses analog spike-like signals. It's very different type of signals. These signals, the clock speed of the signals in digital computers are at gigahertz. Okay, we are talking about 3 to 10 gigahertz. The human brain signals are operating at a much lower frequency at about 100 hertz. Okay. Similarly, if you consider the human brain consumes a much lower amount of power. One human brain consumes about 20 to 25 watts of power. Okay, the power consumed by just one chip, as one NVIDIA's microprocessor chip, has approached kilowatts now. Okay, imagine combining thousands of NVIDIA chips together to make their ChatGPT cluster, for example. You are talking about, hundreds of kilowatts of power. Okay, hundreds of kilowatts to thousands of kilowatts, almost a megawatt of power. So, what I'm trying to say is that um, ChatGPT or artificial intelligence requires a lot more power, and it is still not as smart as the human brain. Even a 5-year-old baby can very easily distinguish between who's mom, who's dad, and can recognize if there's mom there, dad there, or a stranger there. and can also recognize very clearly differences between the cat and a dog or a mouse or different types of cats. To a human brain, this is extremely simple tasks, can be done in extremely low power. Trying to do these image recognition tasks with AI, sure, ChatGPT can do all this very well now. Okay, these are basic tasks, but it can do very well now. They are still extremely energy intensive. So, what is it that the human brain does that is so energy efficient and it takes so much of computing power for artificial intelligence software to do it? I think this is a very important fundamental question to ask. And if we can answer that question and then build computers very similar to how human brains function, you could potentially go to a new paradigm of computing which is extremely energy efficient and works just like the human brain. Okay. So people have tried to do this. Okay, these are very early stages of these things that actually make or wire up silicon to make them signal similar to how human neurons will signal, right? So although you can see the complexity of the circuit is quite large, for each circuit you will need about 7 or 10 transistors, right, to make one human brain neuron type spiking response. There are companies like Intel and IBM. They have actually made chips. Intel has a famous Loihi chip. IBM has a North Pole chip where they have connected millions and millions of these neurons together to fire, just like the neurons fire in the human brain, and see how they can do better computing with that. It is in these kind of chips that people think that if you were to replace these kind of circuits with memristor-like memory devices, then it would truly start functioning like the human brain. And this is where a lot of current research is actually going on. So I'm coming towards the end of my talk. There are a couple of videos, but let me give you a tiny flavor of what modern AI chips look like, because there is a lot of hype, a lot of excitement around AI. So I'm going to take NVIDIA's chip, for example, right? So NVIDIA's this is, I think, H100 processor. As you can see, it almost always has this kind of shape. This is the core or the heart of the chip. The box in the center, this is actually your GPU or CPU core. Okay, and then on the sides of it, right, are what are known as high bandwidth memory or HBM DRAM devices. Okay, so these HBM DRAM devices, they are there on all sides. They are the ones that are storing the data for the model, and access the processor can access it at a very fast speed. They are all connected on this layer known as the interposer layer. The interposer layer is also silicon based, and there are like bunch of wires running through this layer. Okay. So the interposer contains the CPU, GPU, whatever processor died. There are billions and billions of transistors, hundreds of cores in this. Then there is the HBM DRAM. So here is a cross section cut that I'm showing you. And each HBM DRAM die has a tower and towers of memory devices. These tower and tower of memory devices are connected to each other, known as TSV or through silicon vias. These are via contacts, and they are all bump bonded to each other. Ultimately, the interposer is also bump bonded to a package substrate, and this is the package, for example, right? The blue region at the back is the package. So as you can see, it's extremely complex. There are many layers of computing devices, and every stage has hundreds and billions of transistors. So it's become quite complex. It's not like the simple CPU anymore. It has become quite a big computing engine, if you will. Okay. So with that, I'm going to like play this very last video over here. This is a video describing how what is inside AI chips and how Amazon and other companies are testing, packaging, and then evaluating AI chips for their next generation artificial intelligence hardware, such as inference hardware or training hardware. Okay, so let's play this video, and then I will conclude and we can take some questions.
At a time. One step ahead. Watch your step. Step it up. What do you say? Taking the next step with the bullet in your hand. Your whole financial picture and path forward. All with now.
Over the last year, everyone has been talking about
Generative AI. Generative AI.
Generative AI.
Generative AI. I'm like, wait, why am I doing that? I just wait for AI to do it.
driving the boom are AI chips, some no bigger than the size of your
You're not able to hear the sound of the video?
No, Professor, no audio.
Okay, there is no sound. Wait, let me see if I can. How about now? No audio
No,
yet.
Professor.
Okay, let me see how we can solve this issue. I've embedded the video, so in principle you should be able to hear it, but select a microphone, select a speaker. How about now? Are you able to hear sound? No, okay, it's not audible. Yeah, I don't know. Why is the sound not there? Maybe let me try disconnecting my phone and then starting again.
Amazon's chip lab in
How about
Austin,
now?
Texas, where the company designs AI chips to use in
Yes, it's
AWS's
working,
servers.
Professor.
Right out of manufacturing.
Okay, so if you can hear the sound now, then I'll start the video again, okay?
Yes.
Generative AI.
I'm like, wait, why am I doing this? I can just wait for the AI to do it.
Driving the boom are AI chips, some no bigger than the size of your palm, and the demand for them has skyrocketed.
We originally thought the total market for data center AI accelerators would be about 150 billion, and now we think it's going to be over 400 billion.
As AI gains popularity, some of the world's tech titans are racing to design chips that run better and faster. Here's how they work, and why tech companies are betting they're the future. This is the tech behind AI chips. This is Amazon's chip lab in Austin, Texas, where the company designs AI chips to use in AWS's servers.
Right out of manufacturing, we get something that is called a wafer.
Ron Diamant is the chief architect of Inferentia and Trainium, the company's custom AI chips.
These are the compute elements or the components that actually perform the computation.
Each of these rectangles, called dice, is a chip. Each die contains tens of billions of microscopic semiconductors, called transistors, that communicate inputs and outputs.
Think about 1/1,000,000th of a centimeter. That's roughly the size of each one of these transistors.
All chips use semiconductors like this. What makes AI chips different from CPUs, the kind of chip that powers your computer or phone, is how they're packaged. Say, for example, you want to generate a new image of a cat. CPUs have a smaller number of powerful cores, the units that make up the chip, that are good at doing a lot of different things. These cores process information sequentially, so one calculation after another. So to create a brand new image of a cat, it would only produce a couple pixels at a time. But an AI chip has more cores that run in parallel, so it can process hundreds or even thousands of those cat pixels all at once. These cores are smaller and typically do less than CPU cores, but are specially designed for running AI calculations. But those chips can't operate on their own.
That compute die then gets integrated into a package. And that's what people typically think about when they think about the chip.
Amazon makes two different AI chips, named for its two essential functions, training and inference. Training is where an AI model is fed millions of examples of something, images of cats, for instance, to teach it what a cat is and what it looks like. Inference is when it uses that training to actually generate an original image of a cat. Training is the most difficult part of this process.
We typically train not on one chip, but rather on tens of thousands of chips. In contrast, inference is typically done on 1 to 16 chips.
Processing all of that information demands a lot of energy, which generates heat.
And we're able to use this device here in order to force a certain temperature to the chip. And that's how we're able to test that the chip is reliable at very low temperatures and very high temperatures.
To help keep chips cool, they're attached to heat sinks, pieces of metal with vents that help dissipate heat. Once they're packaged, the chips are integrated into servers for Amazon's AWS cloud.
So the Trainium cards will be mounted on this baseboard, 8 of them in total, and they are interconnected between them at a very high bandwidth and low latency. So this allows the different training devices inside the server to work together on the same training job. So if you're interacting with an AI chatbot, your text, your question will hit the CPUs, and the CPUs will move the data into the Inferentia 2 devices, which will collectively perform a gigantic computation, basically performing the AI model, or will respond to the CPU with the result, and the CPU will send the result back to you.
Amazon's chips are just one type competing in this emerging market, which is currently dominated by the biggest chip designer, NVIDIA.
NVIDIA is still a chip provider to all different types of customers who have to run different workloads. And then the next category of competitor that you have is the major cloud providers. Microsoft, Amazon AWS, and Google are all designing their own chips because they can optimize their computing workloads for the software that runs on their cloud to get a performance edge, and they don't have to give NVIDIA its very juicy profit margin on the sale of every chip.
But right now, generative AI is still a young technology. It's mostly used in consumer-facing products, like chatbots and image generators. But experts say that hype cycles around technology can pay off in the end.
While there might be something like a dot-com bubble for the current AI hype cycle, at the end of the dot-com bubble was still the internet. And I think we're in a similar situation with generative AI.
The technology's rapid advance means that chips, and the software to use them, are going to have to keep up. Amazon says it uses a mixture of its own chips and NVIDIA's chips to give customers multiple options. Microsoft says it's following a similar model.
For those cloud providers, the question is how much of their computing workloads for AI is going to be offered through NVIDIA versus their own custom AI chips. And that's the battle that's playing out in corporate boardrooms all over the world.
Amazon released a new version of Trainium in November. Diamant says he doesn't see the AI boom slowing down anytime soon.
We've been investing in machine learning and artificial intelligence for almost 2 decades now, and we're just seeing a step up in pace of innovation and capabilities that these models are enabling us. So our investment in AI chips is here to stay, with a significant step up in capabilities from generation to generation.
Okay, so that basically finishes my presentation. I think we are also at the top of the hour, so it's very close. So let me just summarize and then open up the discussion to questions. The summary of my talk is the following. Semiconductors are the lifeblood of modern information technology, especially when you think about AI. They have always been the lifeblood all the way from early computers to internet, and they have also been the lifeblood of communications. Like, for example, none of the cell phones would have ever become possible without semiconductors, right? It is important to recognize that a lot of the public-facing face of the AI revolution is software like ChatGPT, but this software, the fundamentals of this software were known for more than 20 years. It would have not been possible to implement the software if the chip hardware was not in place. For instance, if GPUs at this scale were never made, running this software would have become impossible. The third thing to remember is that AI chips are power hungry. As you saw in the video too, they have to be cooled, and they have these large heat sinks, and they are packaged in these large containers that actually consume kilowatts and kilowatts of power, and they are currently limited by the bandwidth between the processor and memory. So even though you can make a very powerful processor, if you don't have enough memory and memory's connectivity with the processor, it's going to be very hard. Finally, transformative advances in AI hardware will need new innovations.
in the coming years, and these new innovations are going to happen in novel semiconductor materials and devices because architectural level innovations have reached a saturation point. Okay, so with that, I'd like to end my talk. Of course, I have to acknowledge people who fund my research and who do the research. I don't do any research myself. It's my students and postdocs that do the research. I just give ideas and I look at their data and evaluate them. Our research is funded by various funding agencies, the Department of Defense, Intel, National Science Foundation, Navy, various other companies and so on. And of course, we collaborate with a lot of people all over the world to do the research. And finally, these are some of the papers that we have published related to various subjects. Of course, the AI and electronics related papers are all over here. If you're interested in them, you can just Google these and these papers will pop up. And below is my contact information at the University of Pennsylvania. Again, thank you all for the opportunity. Thanks, Shamant and Mayank and ACAD-Fly for making this possible. I'll be happy to take any questions for the next 20-25 minutes or so. Thank you all.
Thank you, Professor. Thanks for your great insights. Really, really interesting presentation. And we are, I think, at least one up with what knowledge we didn't have to what we have right now. And really, thanks for that. And yes, let's keep the question portal open. All of you can please post your questions in the chat, and Professor would love to, answer your questions.
Okay, so I'm already seeing some questions. Let me try and answer them as soon as I can. Will there be heating issues in 2D chips? Yes, heating issues are there quite a bit. One of the reasons people are going to 3D chips and also using new materials in 2D chips is because of the heating issue. Okay, heating issue has become a big problem with silicon, and that is the reason they want to go to other semiconductors where they consume less energy per unit time, so not as much heat is generated, and they are easier to cool if the materials are thinner. So that's the main reason people want to go to other materials. Let's see, given we are making specialized chips for different AI tasks, what are the benefits that are modular integrated designs in AI chip development? Yeah, it's a good question. We don't know yet how modular chips are gonna change the game. We know for some applications, like for example, for edge AI applications, an application-specific chip is actually better than a general purpose chip, right? But always recognize that general purpose computing is always required too. The application-specific chip may process a model or data coming from a particular sensor in that location, but in order to feed it into general computing information, you will need ultimately a CPU, GPU. So I think it is wrong to think, or somewhat premature to think, that with the development of AI, GPUs, TPUs, and these application-specific chips happening, the CPU will go away. The CPU is here to stay. It will always stay. It will also keep becoming more powerful, just that it will become one of the blocks in the series of blocks of hardware used for computation. Does that make sense? Okay, one more question. What implications do you see of new TSMC Arizona semiconductor plant? Well, the implications for TSMC Arizona plant is more for the US. US has always feared that China would at some point attack Taiwan, and most of US's most important chips that are made in Taiwan's Hsinchu plant of TSMC will fall into China's hands, or they will destroy it before it falls into China's hands, and the whole world's semiconductor supply will get disrupted. So situating TSMC's latest and greatest plant, a copy of it in the US, and getting it up for production de-risks that possibility in the event that China and Taiwan go to a war. So that is the main implication. It's a more geopolitical implication rather than a technology implication. Why are we unable to use graphene instead of silicon as a semiconductor? Well, graphene is not a semiconductor. Graphene is a semi-metal, right? That's the main reason. I mean, people would have loved to make graphene as a semiconductor, but in spite of trying for many years, including myself, I spent half my PhD trying to convert graphene from silicon, semi-metal to semiconductor. It's not possible. It's chemically very hard to convert it into a semiconductor. It stays a semi-metal. Semi-metals cannot be switched like a semiconductor. How is it possible to create semiconductor transistor at an atomic level? Well, that's for a separate program, separate discussion, but the micro and nano fabrication process is called lithography. using lithography, you make patterns which are atomically small on a semiconductor. It's a whole 1 hour long discussion. I can't really answer except for say that there is a whole course on microfabrication and lithography you'll take, where people use light beams and various chemical technologies to etch structures that are just a few atoms in level to make that. How much time will it take to successfully make a 2D chip? I don't know. I don't have a clear idea. I talk to Intel about this almost every month, but nobody has a clear idea of this. There are many fundamental problems to solve for 2D chips, 2D semiconductors based chip. Like the contact resistances are not there yet. The doping profiles are not there yet comparable to silicon. See, remember, even if 2D materials give some advantage, ultimately they have to outcompete silicon on every metric. Otherwise, it does not justify to replace silicon. So they are currently outcompeting silicon on maybe just 1 or 2 metrics, but there are like 100 metrics. Only when they are able to outcompete silicon on all 100 metrics that they will make sense to go there, right? How does factors like temperature affect the semiconductor performance? Well, temperature depends on what application, but if you are considering semiconductor performance for computing, increasing temperature reduces the performance. It reduces the frequencies, increases the power dissipation. It increases the rate at which electrons collide with defects. So that is a bad thing. Temperature must always be kept down. In fact, if you want to increase the performance of your processor, start cooling it with liquid nitrogen or put it in a more cold environment. It will become better. Let's see what other. How can we say that AI is the need of the hour and not affect our future? I don't think I fully understand this question. If you want to rephrase it, I'll appreciate it. What do you think when India will be one of the good processor making country in the world? Yeah, this is an interesting question. People ask me about when will India get into processor, leading edge processor market. I think the answer is probably never, very unfortunately. That's because everybody knows, or at least the leading countries in the world know in the semiconductor space, that this is the key to next generation technology and prosperity. So India will start making, for example, older edge semiconductor nodes, right? So I think 180 nanometer, 90 nanometer nodes production will probably start in India, or maybe it has already started. But getting to this 2 nanometer, 3 nanometer node is going to be really hard. I don't think anyone or the countries that are holding leading edge nodes, US, Korea, Japan, Taiwan, they are going to give access to India to that very easily. The one place that India could make a dent and progress ahead of others is actually figure out on alternative to silicon technologies. On alternative to silicon technologies, if India makes heavy investment, maybe 10 years, 20 years later, there's a breakthrough where India has a leading edge over other countries. So that is where the investment should be. If you try to invest in silicon now, you're too late. You're at least 50 years behind everybody else. That is very hard to catch up. Is artificial intelligence a good combination with computer science for undergraduation? Yes, I think it's a good combination, though remember that artificial intelligence is also a hype wave. It will go down. Computer science is the core foundation. Artificial intelligence is sort of a specialization of computer science, so keep that in mind, right? I would also add computer engineering to this mix, because computer engineering is going to become more important than pure computer science. Is it possible using AI in the video making process, content creation, so that we can grow better in YouTube? Sorry, I don't know this. I don't make YouTube videos on AI, so I don't know. But it is possible in the coming years, people are going to generate entire videos generated in AI. Like, for example, these I forget the name of the models that OpenAI is pushing out, which are video generating models. There will be movies created, there will be content created that is fully AI generated using figures that are also fully made by AI, and that will appear completely lifelike. It's less than 2 or 3 years away, right? What is different in Apple Silicon? There is nothing different in Apple Silicon. Apple Silicon is a foundry service that Apple uses to design its own chips and helps other customers design their own chips too. So earlier, there used to be just one chip making and chip design company, which is NVIDIA and AMD. Sorry, two, right? And there were total 3 companies making chips, TSMC. So my bad. Let me take it back. There were only 2 companies designing chips, which was Intel and AMD, and 2 companies making chips. One of them was Intel, other was TSMC. Now every company is designing chips, because every company feels the need that they have to make their own chips. Of course, not everybody can make their own chips, they can at least design it. Like, for example, NVIDIA does not make any chip. They just design it and send it to TSMC. TSMC actually makes everything. So Apple Silicon is a similar service like NVIDIA, where you can design the silicon with the help of Apple, but ultimately TSMC is going to make it. And this is why TSMC in Taiwan are strategically so important. Let's see. Is AI helpful to study cybersecurity? I'm not sure. I think AI and cybersecurity can intersect each other at some tangent. I don't think they are fully overlapping though. Why is only silicon used? Even silver is good conductor. Silver is conductor, silicon is semiconductor. Remember that. We are looking at semiconductors, not conductors. Silver, copper, all these are conductors. They are used in wires to connect semiconductors with each other. Semiconductors leads to computing, not conductors. In metals, you cannot modulate the conductivity. In semiconductors, you can modulate the conductivity and do actual meaningful computation like ones and zeros as we talked about. Let's see. You mentioned about the electrical usage problem. What about the data problem? Large amount of data being generated because of generative AI. Well, we addressed that problem too. It's the memory problem, right? Unless you have large amounts of memory, you are not going to be able to store all the data being generated by AI or needed for AI to do the computation. What is a semiconductor? Well, we don't have enough time to cover all those fundamental basics in 1 2-hour class, but a semiconductor is somewhere between a conductor and an insulator. Conductor is like metals, copper, silver, gold. Insulators is like glass, for example, or wood. Wood is insulator, right? Semiconductor is somewhere in between. It's neither fully a conductor, neither a insulator. But the beautiful thing about semiconductor, by applying electric fields or doping, you can modulate its conductivity by millions of times, allowing you to perform this digital logic or memory functions and therefore computing. Will AI provide negative effect to us? Well, it's a philosophical question. I don't know. How to make a future in the field of AI and semiconductors, or study AI and semiconductors, pick majors like electrical engineering, computer engineering, material science of semiconductors. There are AI degrees now. My employer offers these AI degrees too, if you want to take those. All right, that's the way you make future in them. Understand, learn about computer hardware and software. Don't just learn one of it, learn and understand both. Just doing one is not enough these days. Like if you're just software specialist, your career will have limited runway. Just hardware specialist, also your career will have limited runway. You have to be a master of both, I think. How do quantum mechanics influence the behavior of electron nanometer scale semiconductor devices? I would have loved to answer that question. I offer a 6-month-long course in my university on that. You are happy to take that course. I'll tell you everything about how quantum mechanics affects the behavior of electrons in nanoscale materials and semiconductor devices. It's a 6-month-long discussion. I offer a full 6-month course on it. Do you think cybersecurity is good? I'm not a cybersecurity expert. I don't know. Sorry. I think it's called Sora, the video generation model. That is correct. Sora is the model of AI, video AI from OpenAI. I don't think it has been opened up to the general public yet, but it will be soon, I think. Can AI be done along with information practices? Again, I don't know. I'm not a career counselor. Professor, what happens to the disk inside a hard disk when it is corrupted? When it is corrupted, a lot of bits have been broken, okay, or a lot of bit information is unreadable. This is because the read and write circuits have got corrupted or destroyed for whatever reason, right? And that is the reason why you cannot access that data, and it's basically data is gone. It's become junk. What is the major benefit Apple gets from manufacturing their own chips? Well, they can control their own IP, number one, if they can manufacture their own chips, and their software or their programs need a certain architecture of chips that is not available in others' chips. And so by doing that, they are controlling more and more of the IP and customizing the chips to run their phones or their software or their applications better. So everybody designing their own chips is for their own benefit. I mean, Google makes their own tensor processing unit too. TSMC, of course, fabricates everything. Yeah. Do you trust AI systems with your personal data? Again, philosophical questions. I'm not the one to answer it. Professor, will AI bring negative effect? I cannot answer that. Is semi-insulator and semiconductor the same thing? Yes, it's a terminology difference. Some people refer, in the older generation, older textbook, people would refer to some semiconductors, semi-insulators, but they are the same thing. That the speed of chips depend on the nanometer technology. If yes, please elaborate it. Yes, the speed does impact on how small you make the transistors. smaller the transistors you make, lesser the amount of distance electrons have to travel, lesser the amount of distance electrons have to travel, faster the speed or frequency they can operate at, therefore faster the computers can operate. It's very simple. The distance you reduce of moving electrons and therefore information, the faster things operate. What are the scopes in the field of AI? Not a cardiac counselor, sorry. Why is germanium not used instead of silicon? Germanium does not have the right band gap, and it does not have a more stable oxide that can produce the field effect, unlike silicon. So if you try to make a germanium transistor, even though germanium was the first semiconductor on which bipolar junction transistor was made, when people switched to field effect transistors, silicon was the preferred choice because the silicon oxide interface is much more stable interface as opposed to germanium oxide interface. That's the main reason. Can we prevent a bit flip due to cosmic rays? Yes, you can. There are very special types of memory devices you have to use for that. And very special type of radiation hardened transistors that you have to use for that. Is Apple competitor in chipping technology? I mean, they are making any great innovation like they are claiming to. I don't know. I don't work for Apple. You may have to ask the people who work inside Apple. I think they are making chips for their own use. They are not making chips to sell to the broader market. That's my take. Nanotechnology uses and excess use of it harmful in our life. Please comment. Nanotechnology is too big of a field. There are positive uses of nanotechnology. There are negative uses. Positive uses are the COVID vaccine was made out of nanotechnology. All the modern microchips and processors are made out of nanotechnology. So these are all positive aspects. There are negative aspects too. You can make certain types of drugs, chemicals that are incurable. You can specially design viruses that could cause new pandemics, right? Because using nanotechnology, so these are negative things, right? Depends on what you want to do with it. Every technology has positive and negative consequences, like nuclear technology. Could AI potentially develop its own language and form of communication? I don't know. I think it's too early to predict that. You have to read to AGI before that happens. Professor, what are some of updates on TSMC's 2 nanometer chipsets? I don't know about any updates on 2 nanometer chipsets. All I know is the 2 nanometer process is appearing closer and closer to production. I think it has already gone in production for some customer. I don't know who yet and what actual device in, but I know TSMC 2 nanometer process has reached production quality yield. Or that's all I can say. Can antimony be used to make chips? Antimony is a semi-metal again. Sorry, no semi-metals in chips. Okay, looks like we're at the end. How does Apple make its chip to work better with its own software like Final Cut Pro? These are very detailed hardware level questions. I don't know, right? I mean, there is thousands of patent IP that goes into every processor. Many of these things are not revealed. It's arrangement. At an architecture level, there is again a full 6-month course you can take on computer architecture or VLSI. That's where all these innovations come in. And how are you arranging circuits? How are you arranging logic circuits to memory circuits? How are you using the read and write circuits to feed data from the memory bus lines or the data lines into the processor? How are the logic gates arranged? How are you fragmenting data? All these innovations that are there. There are so many patents, so many trade secrets in many of these things. So how does Apple make work history better? If I knew, I would become richer than Apple. How is semiconductor needed for AI? Well, the whole talk was about it. I don't know if you were paying enough attention, but semiconductor is the base of AI there. Whole talk was about it. What challenges arise in scaling AI models for real-world application? Well, AI models are already used in real-world application. Scaling of these models, the challenges it presents is that the more you scale the model, the more the parameters are scaling, the more parameters are scaling, the more intensive it is becoming for the hardware to handle those models. So we have to figure out a way to make better and better models without scaling parameters at the same rate. And this we don't know yet. This is a fundamental software issue, I feel. I don't know if a big breakthrough will come in this area or not. Most people think there won't be any big breakthrough in the area, but you never know. There are very smart people working on the software side too. Do you have any insights into whether how these chips development and AI chips are affecting edge computing and decentralized AI, especially with things that require real-time processing? Yes, so there are some AI chips that are used at the edge. They certainly don't have these hundreds of cores of GPUs, but they can do very limited amount of inference and processing at the edge. They are already going into some smartphones. I think some of the latest and greatest Apple smartphones have it. For example, you can already see in some of the smartphones, if you start clicking a picture, it will immediately highlight the face of the person that you're trying to capture the picture of. It can even recognize the person if you have told it to recognize the person. For example, in my phone, in my Google Pixel phone, after sorting through all my images, it now directly pops up and shows me these are the images of your wife, these are the images of your son, right? It just automatically labels them. So this is basically edge AI working inside your phone. How do you get interested in semiconductor? Well, I was a metallurgical engineer by training, but I focused on electronic properties of metals. From electronic properties of metals, it became electronic properties of semiconductors. When I went to do my PhD, and then one thing led to another, and I started making semiconductor devices. Then I did my postdoc in photonics at Caltech, and now I'm a professor of electrical engineering. So I'm a self-taught electrical engineer. I don't have a formal degree in electrical engineering. All my degrees are in material science or applied physics. So I self-taught electrical engineering myself. So that was a great learning experience. Sir, in computer field, which one field is most demanding field? Sorry, I'm not a career counselor, but demanding fields change with time. There are waves in which fads go in research. Some things stay evergreen, like electrical engineering stays evergreen, computer engineering, computer science stays evergreen. These are things that never change. All the fundamentals of all new technology fads, you see, they are embedded in these the old and evergreen disciplines. What challenges your team currently working towards solving? That's another 2-hour talk. If there is a chance later, I'll give that talk, which is fully on my research. It's too high level though. You have to know a lot more about semiconductors, electronic band structures, and things like that to understand that. Even photonics and electromagnetics need to know a lot more of the basics of that to understand the research that we are doing. Will AI need pre-programmed software? I don't know about that. I don't even understand the question fully. AI can program the software for you. Will AI itself need pre-programmed software? It's unclear to me. Depends on what level of AI we are talking about. Professor, how can a data recovery software recover corrupted data from non-volatile memory? Sorry, I'm not a computer hardware store guy. The data recovery software will basically, I don't exactly know how these softwares operate, but what they would do is that they would change the read-write codes for every memory bus line. And that way they can at least access to parts of the memory or data that are not like fully corrupted. Professor, have you gone to MIT for further research? Well, I have friends at MIT. I collaborate with MIT. I haven't gone to MIT. I went to Caltech. Caltech is equivalent to MIT. It's much smaller university, but much more focused. Can you elaborate what field, Professor, you're working on research right now? Again, as I said, it takes another hour, 2 hours to talk about all of my research. What type of math is used into this type of industry? Mostly linear algebra. You need to know a lot of linear algebra. Of course, calculus for semiconductor research, calculus is very important, but linear algebra is what drives AI. Most of AI is linear algebra and matrix multiplication. Okay, I think we are coming at the end of time. Shamant, is there anything else I should be doing before I sign off?
Nothing, sir. I think it was wonderful, and I think the overwhelming response from the students have been really, really good. I think we have had like almost, as per my last count, around 25 to 30 questions, which is really good. That speaks a lot about their engagement and how much students have understood and how intrigued they are. And yeah, nothing much, sir. So if all the questions are addressed, I think you can take your leave, and I'll continue for next
Okay.
10-15 minutes. Yeah, that's it.
All right. Thank you, Shaman. Thank you all. Take care, everyone. Hope you enjoyed and hope you learned something
Yes,
from
everybody
this. I
stay
think that was
back.
the main.
Everybody stay back on the session.
All right. Take care. Bye-bye.
Have a great day, sir. Bye-bye. Yes. Thanks a lot, everyone, for staying patiently till the end of the session. For the next 10 minutes, I'll be clearing your other doubts, which couldn't be clear from sir regarding the what branch to choose. Of course, I'll at least try to clear those doubts, and how ACADFly, how Physics Wala has been helping students throughout. I'll be giving you that kind of idea, right? So this will be an interactive session where I'll be giving certain polls, certain questions, which will be projected in your screen. You have to choose one of the options. And yeah, that's it. Well, once that is done, I will be understanding what exactly you are requiring and what exactly it will be a completely interactive session. That is all I can say, right? Fine. Let me share a particular PPT to showcase it. Just wait for a minute. All right. Yes. Is my screen visible? Hope it's visible. Right? Great. So, yes. So, introducing ACADFly, powered by Physics Wala, guys. So, this is India's only profitable edtech company, founded in 2014 by Alak Pandey sir, as you all know. Currently, we have a quick, this is a quick introduction so that I can go towards the other part. 40 million registered students we have, and 20 million plus YouTube subscribers we have, and 18 plus academic disciplines, basically in K10, K12 for 10 till 6th standard to 12th standard, and also for CAT, GMAT, GRE, UPSC, the government exam, and the abroad sector. That's where we come from, ACADFly, where we deal with the students who are interested to explore the study abroad landscape, right? So ACADFly, as I was saying, so this is our particular, mission, that is to transform the study abroad landscape in India. We are focused on achieving twin goals of making global education accessible to all the students by providing the best academic outcomes for the students, right? So where either you go out, out of India whenever you go going for that particular purpose, and also for global faculties who can help you while you're being in India. Both of the other way, we'll be helping you out. So a quick introduction of our team. So this is Mayank Sharma, our senior VP from Physics Wala. He is a IIT BHU alumni. He has done his MBA from IASC Business School from Barcelona. And this is me, Shaman. I'm business lead in Physics Wala, and I come from IIM Kozhikode MBA, right? So what exactly do we do, right? So that's the interesting part which I wanted to share. So we offer diverse range of study abroad immersions to the students, right? We partner with the global universities which are designed to enhance educational experience. So we have dual enrollment program for you. We have Babson Bootcamp program for you, which will be conducted in Bangalore this year. Babson, I'm sure every one of you know, it's ranked number 2 by Wall Street. It's ranked even higher than MIT and Harvard, Babson University. And Babson Bootcamp will be also conducted in Boston next year. I'll be giving a wider idea of what we are trying to do. This is just a topic, and we also have ACADFly Connect. We just had the session, that is ACADFly Connect, where we connect the students in India, 9th standard to 12th standard students in India, with the top global faculties worldwide, right? Like right now, we had from a professor from Ivy League, UPenn, Deep Jariwala. So like this, every week or every alternative week, we have such sessions which will be connected for the students to enrich your particular skills and knowledge. And we also provide counseling support for students, which I was seeing in chat, most of you are having major doubt of what exactly to do post 10th, post 12th, right? Which branch to take, where to go, which university, etc. We do that too. All right. Next. So coming to what is dual enrollment, right? So before that, I would like to ask a particular question. Before that, I'll just 1 second. I want to raise a particular poll. Archit, are you in the call? Can you make me co-host? I'm unable to raise the poll. Archit? Archit, are you on the call? Just 1 second. Archit, are you in the call? Just give me a minute. Yes, everyone. So my first poll is this. So are you considering study abroad after your 12th grade? So please start answering this. I'll give you further 5 to 10 seconds more to answer this. So quickly, let's. Yes. Yes. No, not sure. Whatever you have in your mind, please quickly answer this. Okay. Everyone, we still have around 10 students yet to answer. Hope all have answered. Okay. Quickly answer, guys. This is very much important. Okay. Fine. I'll end this poll. Great. My next poll would be this. Which country are you most interested in for your higher education? Quickly answer, guys. I'll end this poll in next 10 seconds. Which country are you most interested in for your higher education? It's US, Canada, UK, Australia, Germany, India, or if there is any other, please do choose that option. Great. Let's end this poll. My next question is this. What kind of foreign universities do you aspire to study in? Like Ivy League, top 50 global universities, affordable foreign education, or top ranked Indian universities? Because from this question, I'll come to the dual enrollment program, which I was talking about. Ivy Leagues are, of course, the top 10 cream universities. Like we today had the professor from one of the Ivy League, University of Pennsylvania, UPenn. Top 50 global universities can be UCLA, Berkeley, John Hopkins, right? Top 50 and affordable foreign universities which provide good education. Of course, there are multiple universities as such, which might not be in the top 50, but definitely they have good exposure. And top ranked Indian universities, if you're looking at. Great. So I'll be ending this poll in next 5 seconds. So quickly answer, guys. All right. Hope all have answered. I'll end this poll. Yes. Thank you. Now, coming back to our slide. Hope my screen is visible. Right? Okay. What is dual enrollment? So dual enrollment allows high school students between 9th standard to 12th standard to take college credits taught by university certified instructors. So students have the ability to earn up to 24 university credits while in school itself, which will be equivalent to freshman year. So their dual enrollment has 24 credits which needs to be fulfilled to skip the first year of the bachelor's. So each course will last between 16 to 15 weeks, which basically has 37.5 classroom hours, which can be taken concurrently. So here, I have an assumption like I'm a 9th standard student. I take dual enrollment program. I have to complete 8 subjects by 9 to 12th. Once I finish this, post 12th, I'll be directly admitted to second year in a foreign university. That is dual enrollment, right? That for there are a couple of options in dual enrollment which I'll be coming into. So major advantages: minimum of 1 year can be skipped. That means 1 year of time, money, energy once you do this particular course while being in school itself. The second option, I'll just come to this. So first is dual enrollment program from Marquette University. Benefits of DEP, dual enrollment program from Marquette University. We have 2 programs. First is it equips every student for a successful start in the university. If I take this post 12th, I'll be admitted directly to second year. I'll skip the first year. So I'll be way ahead of my peer whom I was a part of when I was in 12th standard. So I have a head start, right? That's the first benefit. So I'll be finishing a 4 year of bachelor program in just 3 years. Even the placement opportunity, everything also I'll be getting in 3 years itself, right? Second advantage, I can save up to 67,000 US dollars, which roughly comes up to 50 to 60 lakhs if I take up this dual enrollment program. And of course, every if I have to go to any abroad university, I'll have to give GMAT, GRE, SAT, etc. Right? So once you do this program, you can skip all those tests and all the application requirement. Another advantage is you'll have guaranteed admission and scholarship for certain universities. Guaranteed admission. If you finish this, you'll have a guaranteed admission and guaranteed scholarship every year. And it will be basically provided by ACCP accredited credits, which can help you to transfer these credits. So this is the first advantage, right? From the first dual enrollment program from Marquette University. Second, what are the benefits of doing a dual enrollment program from UPI? This is the second option which you can have. First, you can earn university credits while studying at school itself, considerably slash your UG and PG tuition fees, right? And third, you can build a pathway for up to 10 years of residence in the US via OPT. Fourth, you can have direct admission in second year or even third year. That's the differentiating factor here. You can also have a direct admission in second or third year in the bachelor's in the foreign university. And you can transfer your credits up to 1,500 university via NCC RS. And you can also have academic and logistic support and in case the credit transfer fails in this particular, you'll also have 100% refund, right? And also you can save up to 2 years of tuition fees and residence fee, because you'll be doing this complete course in India itself, right? So that's why you can save up to 2 years. So basically you can save your time, money, and also you will be getting a complete degree of the university which you will be going to. Exciting, right? Now is the time for my next poll. For 1 second. Now that we have you can earn university credits while still in school via dual enrollment, would you be interested in learning more about dual enrollment? Like what exactly it is, how to explore it, what kind of options do you have? If you're interested to know more about these details, do share me your consent. I'll share the details to you. It will be sent to you over mail or WhatsApp so that you can know more about it. That's the only reason I've raised this poll, so that I can have a complete idea that you are interested to know more about this dual enrollment program and potentially choosing this pathway post 12th grade. Yes, I can see quite a lot of you interested in this. This is really exciting. Good. Okay, I'll be closing this poll in next 5 to 10 seconds. Hope all have answered. Still around 5 of you are yet to answer. Please quickly answer. Now that you know that you can earn university credits while still at school via dual enrollment, would you be interested to learn more about the dual enrollment program? Yes or no? That's it. Great. I think I'll end this poll and I'll continue with my PPT. So we have Babson Bootcamp 2. Babson, like I said, it's ranked 2 by Wall Street, above Harvard and MIT. So we have 2 Babson boot camps. This year we are conducting one Babson boot camp in Bangalore. Next year in Boston. The students can participate in both who are interested. The duration will be 4 to 5 days in Bangalore. For Boston, it will be 10 days. 9 to 12th graders can participate. Here, basically, you'll have a Babson faculty. In Bangalore, if you're participating, you'll have Babson faculty who will mentor you in Bangalore, who will be traveling from Babson, Boston, who will be traveling to India, Bangalore, and they will be guiding you. If you are interested to go to Babson, student will visit Babson College in Boston in the second option next year. So here you'll have intensive course on entrepreneurship. So if you're choosing Boston next year for 10 days, you'll have a proper exposure of international college about what is the lifestyle, how is the teaching, how is the infrastructure, what is the exposure, each and everything. There are 2 options which you get, Bangalore and Boston, right? Cool. Now, so in Bangalore this year, it will be in December. Just quickly telling you, next year it will be during your May or June when you have your vacation. Great. So regarding Babson, I'll be just launching this particular post. In other news, we have also partnered with Babson College and are promoting their boot camps across India. Babson was ranked 2 by the Wall Street Journal as per the WSJ and College Pulse 2025 Best Colleges in the US report, surpassing even MIT and Harvard. Would you be interested in attending the Babson Bootcamp in Bangalore this winter and the Babson Boston during the summer of 2025? If you're interested to attend either of those, please go ahead and mark your interest. Accordingly, we'll share you the details. If you're interested to take this Babson bootcamp in Bangalore, you can definitely mark. If you're interested to go Boston next year during the summer of 2025, you can also mark yes for that. We'll share you the details accordingly. All right. So quickly mark your answers, guys. Great. Fine. Let's end this poll in next 5 seconds. I hope all of you have marked. Great. I'll be closing this particular poll. So last but not the least, we have AcadFly services. There are two services. One is counseling service and another is ancillary. In counseling, we have personalized counseling, application support, test preparation, visa guidance, and pre-departure support. And ancillary, we have loan, finance, accommodation, forex, and flights and insurance facilities. All right. Great. So this was the last slide. Post this, I'll be sharing a QR code quickly. Before that, last two polls I'll be just sharing right now. You can quickly mark your answer over there. In case you are interested of studying abroad, would you be interested to speak with a study abroad counselor who can help bolster your profile and guide you on your journey to your dream university abroad? With AcadFly, we have got you covered for your entire study abroad journey, from counseling, application, visa, loans, forex, accommodation, and also post-study jobs assistance. So whosoever are interested, so please start marking. If you're interested to know more about this, definitely you can go ahead and mark your interest and we can share the details accordingly. If you want to know, in case you're interested to know more about the counseling part, like if you're confused about the university or this, which country and how exactly to apply visa or applications, loans, forex, accommodation, etc., each and everything, end to end, anything if you would like to know, we'll share you the details. So please mark your interest or your answer accordingly. We'll send you the details. Quickly mark this, guys. We'll just wrap it up in next 3 to 4 minutes. Okay, I'll be closing this in next 5 seconds. I hope all of you have answered. Great. Okay, fine. Quickly done. Last but not the least, regarding today's session from Professor Deep, how exactly you have, how much you have taken off and each and everything. We hope you have enjoyed the free introductory session with Professor Deep. Would you be willing to continue and complete the AI course by Professor Deep and receive a course completion certificate? So please do mark yes, because of course today all of you will be getting the participation certificate. Once you go ahead and finish off the course will, of course, it will have further 3 to 4 hours more, and there'll be a nominal fee for that. It will be ranging from around 1.5 to 2,000 max. So nominal fee will be involved if you want to have the complete course to be done. So please mark your interest accordingly. We'll share you the details and we'll share you the link, and you can click on that link and you can participate. So you'll be awarded a course completion certificate by Professor Deep and of course by Physics Wala, and also you can pursue your career accordingly. So yes, hope all of you have answered. This is really good. Almost all of you are interested. I hope today's class was intriguing for everyone. And I'm glad. Thank you, everyone. I'll just, next 5 seconds, I'll close this. All right, 1, 2, 3, done. Great. I think we are done with all the polls. I'll quickly share the feedback form and your details which you have to fill. So quickly scan this QR code and fill your feedback and your personal details, because we will be mailing you the participation certificate accordingly. So please, go ahead and scan this particular code and start filling the form. I'll also send it in the chat for everyone. Okay, if you can't scan, then you can click on this particular link. 1 second. Yes. You can click on this particular link and start filling the form. I've pasted in the chat. In case if you can't, you can always scan. You can scan, basically how do you scan? You can take your phone camera and just point it towards the QR code. It will take you to that link. You can either scan it or you can click on the link. Either of the options will work, but it is mandatory for everyone to, fill this form. If you don't fill it, of course, you will miss out on the certificate. So please do fill it and please give your feedback of today's session and of course your details so that we can get back to you accordingly. Right? Hope all of you have scanned. Still, if you have not, I'll keep the scan, and even the Google form is already pasted in the chat. Please use one of these. If anyone is facing difficulty with this, please do post in the chat. I can definitely see and help you out. Hope it is usable for everyone. Fine. All of you are done. If you're done, you can show a thumbs up in the chat, or you can just post in the chat, it's done. And accordingly, we'll get back to you. And it was wonderful having a chat with everyone. I wanted to take a quick photo with everyone if it is possible. Archit, if you're in the call, can you allow everyone's, camera so that I can take a quick screenshot of everyone's participation? All of you can on your camera, and I think it should be visible for me. Archit?
Yes, sir.
Yeah. So can you just make it possible for all of you to be visible in the
Yes.
gallery? All of you just on your camera. We'll take a quick snap. Meanwhile, you can fill the form or, So once you fill the form, let me repeat, you will get your participant certificate by next 2 working days. Hopefully by Monday or Tuesday, you'll be getting in your mail itself the participation certificate. All of you can on your camera. We can just take this is our way of taking selfie, right? Now that we are all not physically together. So yeah. Hi Ayush. Archit, can you allow more people?
Sir, I am allowing all of them, but they are declining the request.
Acha, understood. Whosoever is interested, you can definitely accept, and we can all take a quick selfie. And please do note the particular feedback form link. I repeat, it's very much important for all of you to fill it so that we can get back to you. I'll also paste our LinkedIn link so that you can go and like our post. I pasted our LinkedIn. Okay. Great. So the photo, whatever we'll be taking, it will be posted in LinkedIn, guys. So quickly just accept it and let's move ahead. All right. Great. Fine then. Let's end the call. And I've taken the screenshot and glad to see you everyone. And I hope all of you had a good time today and had something new to learn, and hoping to see you all soon. Great. All the best, everyone. Thank you so much. Bye-bye.
Thank you, sir.